Again, this is Claudio from expertfea.com. Today we are celebrating 13 years of presence on YouTube and online. And yes, let me share my screen. This is our website, and in 13 years we're offering already solved simulations, FEA tutorials, mechanics, books, webinars, and yes, FEA support. So be sure to email to us following the contact page. Today I am going to discuss a topic that is very, let's say, unknown, and very few people touch it. And the topic would be something like coupled Eulerian-Lagrangian. With the main use that we have, and we can touch the very interesting domain and important domain of fluid structure interaction without using very difficult CFD and then following them with static or transient structure. So let's see what this entitles. Okay, I will drag and drop an explicit dynamics case. And here I will insert. Let's create from start. I would like to take it from zero, from scratch. What I will do is I will go from the very beginning with something very basic, and I will evolve into something refined and correct. Because in the beginning we'll just model a sphere and a tank filled with water. Then I will begin to refine, because the first approach with solids and let's say Lagrangian bodies will not be correct. Then I will go more and more in detail in order to make a correct simulation. So let's start with the sphere, because everyone does it. Why not? I don't know how much, 100, 200, 500 millimeters. Let's make it pretty big. All right. And as long as we're here, let's also model the water tank, if possible. Because I don't want to have the sketch coming out from the sphere center, I prefer to make a separate plane. Let's see if I can. All right. So let's move this plane. Okay, let's do it like this. I will somehow create a rectangle. I don't care about the dimensions too much. Well, now on a tutorial level, something basic. So let's do something like this. Maybe keep the square approach. 1200 here. I press tab, then 1200 here, and it is a square. It's not perfectly centered. Let's make it, let's say, symmetrical. This means here we should have 600, and here we should have again 600. Now it's perfectly centered. The sphere is perfectly centered. Undo, because I would like to make like an offset walls of the tank. Yes, we have this command offset curve. I will select the entire rectangle. Then maybe 25, the thickness of the tank. All right. We have the walls of the tank. I think we need to make it much bigger. Yes. How much should we go? How much should we go? Let's see. How much should we go in order to have something useful? I mean, the quantity of water that will be touched to have a proper depth for the water. Yes. Let's bring this above. Yes. Then we don't need the tank to be too deep, because we're wondering more on what happens at, let's say, close to the surface of the water. Yes, something like this. All right. If we select these edges from the inside, only the inside edges with Control pressed, we have here the command called fill. This command field has created a surface, and this surface will be like the bottom of the tank. If I drag it right now with pull, then it will attach, okay? But there will be this difference. There will be this difference. So let's also pull with this face. And you understand now, yes? 25 was the thickness of the tank. All right. So we have all these. You know what? In order not to increase the scale, should I increase the scale of the tank? Let's firstly decrease the radius here, maybe 150, 200. Okay, 200. And I will. Should I do it like here, or should we come from above with this? Let's come from above, because we have seen this approach, yeah, angular, let's say. For our example, let's come from above, okay? We will start with the simple. This is a simple approach. Then we will kind of complicate it, because I would like to simulate the airplane touching the water, and hopefully it will also lose its engines. So we will start from very simple to more advanced, okay? So we need water inside. The easiest way to make the water is to click the bottom of the tank, and I will pull, but I will select here no merge. Yes, because otherwise it will immediately fuse with the tank body, okay? How much do we go? Something like this. 300 millimeter. Okay. So if we go in section, I will click this plane, then move and rotate it. Double click here on the arrow. Double click. Then we go in section mode. Look here. It's still merged. Why do you merge it? It shouldn't, the water shouldn't have been merged. All right, let's see if we have undo, okay? Let's see if we have another way to do it. Hit again, no merge. Maybe add. All right, add material when you pull. Let's see. 300 was, yes? No, we still have two bodies. No problem. Undo. There is also this solution. Copy paste, Control C, Control V. We have this surface, yes? In order to avoid that it will merge, I will click here, no merge, on the surface, yes? And hopefully it will make a separate body, hopefully. You see, now we have three bodies. Let's go again on the section view. This means we'll rotate this plane. Then we are going for the section mode. Look here, three bodies, all right? This is the water, the tank, and the sphere. Everything right now is a solid body, a solid part, all right? Remember this. Let's save this simulation. Stream 5, this is an anniversary stream. Water tank. Water tank. Let me also write couple Eulerian-Lagrangian. All right, I will keep space claim open for a quicker import. Let's go a little on the engineering data. After I will see if there is any question from my audience. All right. Hi, Siti Hassan. Hi again. I wish I could watch your live stream, but it is past midnight. No problem. The stream remains. No problem. I'll watch the recording. Yeah. Thank you. Sure. How? Thank you. Go to sleep. The sleep. The stream stays. No problem. Thank you, Shasha. Let's put a heart here because he's a returning viewer. Good night. All right. Back here. Do we need to keep the structure still? Let's leave it. And we will do something, as I said, default, because I would like for you to understand the logic. All right. We'll start with the basic, then we will make it more refined and correct. We're going for general materials. It's not here. Then let's not go here. I'm looking for water, sincerely, all right? I can create water, but let's not complicate. We find water in explicit materials. In explicit materials, you find very wide domain of numerous examples of materials. W is water. Let's go here. A little, should we take a glimpse of the properties? We have density and shock equation of state. Here we have also some tensile pressure failure. And here we have polynomial equation of state, all right? So let's just go with the first one. We have the steel, we have everything. All right, for a faster solving, let's use aluminum because it has lower density and it will solve quicker. As I explained in a previous slide, refer to mass scaling and Courant-Friedrichs-Levy And there you can see the fact that a lower density influences the time step. It will increase the time step, thus extending the solving, shortening the solving time. So aluminum alloy. And here, let me delete this steel. We have the proper materials now. Double click. It will load fast because I have space claim opened. After the mechanical window opens, the geometry will be loaded very quick. Okay, it's done. In order to center our view, we have the zoom extents button F7. All right. So this is what we're beginning with. It's safe. Now we're going to apply the firstly rename F2 ball, F2 tank, F2 water. The ball, I said, it's made of aluminum. Also, the tank should be made of aluminum. At this moment, let's leave them flexible, because I also would have the desire to make them rigid, because sincerely, we don't really care about them. We don't care about the behavior of the water, all right? Water, and we are leaving default here, reference frame Lagrangian, all right? This is default, because in the future, we will change it to Eulerian, and yeah, let's also change it to particle in a few minutes. All right, let's leave it default. This is a beginner simulation. It's and with beginner errors. All right, this is an error. Okay, having water Lagrangian. These having Lagrangian frames, it's just normal. They are solid bodies, solid parts. Their structure. Okay. So, regarding the connections, we have some contacts. Sincerely, I'm not interested in these contacts, all right? There is a contact between the water and the tank. Do not leave these contacts as beginners do. Only leave the default frictionless interaction body. All right. Let's go to capture curvature now, and the quality I choose low here in order to have a very basic, very fine, very coarse mesh. Generate mesh. So this is the mesh. Sincerely, for my taste at this moment is kind of too fine for me. Let's make a section. I'm clicking on the arrow, section planes, new section plane, and the middle is something like here. Let's change the direction with edit section plane, click the hidden line, and we have something like this. In principle, you know, it's all right. Let's solve it, and we will debug it afterwards. Okay, if we need to refine it. Sincerely, my idea is to have a very fast solving simulation, because I want to iterate more and repeat the simulation with different parameters. What we can also do, let's move it closer to the water. All right, to move. the sphere closer to the water. Model, part transform, click the sphere, right click, something like this. We're going here on details, apply, and offset about the y-axis. You can see the green axis is y, yes? I hope you can see it. Can you see it? Is my, yes, you can see it, okay. It's not, Mr. Light, hello, greetings, yes, greetings. I don't know if master, but yeah, greetings, thank you. And Murat, he retracted his message, okay. Hopefully he will give an even nicer message, yes? Hi. Thank you for the audience and your interest. I said that we are going to offset it, yes, vertically. How much should we? Maybe 70 millimeter with minus. I know everyone wants to have a larger distance in order to see the impact, and but normally it's much useful. It's more useful if we have almost contact, okay? Normally we can have zero distance, no problem. Minus 150, perfect. Right click, transform. You can see the correct position here. When you click mesh, then everything is correct. All right, let's think at this moment about some boundary conditions, all right? The first boundary condition would be an initial velocity. Initial velocity, click here, we have the part. The direction is vertical on the y-axis. It didn't work. Why? Because I am selecting a face. Yes? And this, the initial condition loads, they require a solid selection, a body selection, which means right click, cursor mode, body. Click body, apply. All right. We can either assign components or vector, but now it's very easy if we right click cursor mode, face, maybe assign a vector normal to this face. Direction, apply, all right? We're going to change the direction by clicking on the black arrow here, apply. We will see the arrow again once we assign the value, the velocity value, all right? New. I would like to make a small calculation regarding this one. Let's make a small calculation. Section planes. Let's measure the distance. The distance that I would like the ball to travel would be around maybe 150 or 200 millimeters. Let's say 200 millimeters. Let's just say it, okay? Even though it's 200 millimeters. Then we'll have something like this. Blue pen, all right. I need let's make like a target end time, all right? A target end time. So I need in 0.001 seconds, I need the ball to travel 200 millimeters, all right? Then how much it will travel in 1 second? I want to apply the velocity, yes? This is why. And the velocity is millimeters per second, yes? So x is, let's make the multiplication. I will show it very clear, very basic, and very understandable. Multiplied with 1 second, this is second, not 15, over 0.001 second. Always keep the measurement unit, because now you can simplify it. Yes, you can reduce it. This is not the dollar sign. The dollar sign has 2 lines. All right. So the result will be, we can do something like this. 2 at the power multiplied with 100, all right, 2 at this power over 10 at the power minus 3, okay? Then x is 2 multiplied with, we can make the difference here, okay? This means it will be 10 at the power of 2 minus 3. All right? Millimeter. This means it will be 2 multiplied with 10 at the power 5, yes? Because 2 minus minus becomes plus, 2 plus 3 equals 5. 2 at this power, which also means, just for fun, 200 meters per second. And if you multiply this with pi, you have around 6 to 8 kilometers per hour, if I'm not mistaken. Let's see. 200 meters per second, 2 kilometers per hour. Yeah, the multiplication is 3.6, okay? It's related to the number of seconds in an hour. Yes, so 3,600. I'm sorry for my overlap. I didn't use such calculations in some time. So let's write here something like multiplied with 3.6, and it will result 720 kilometers per hour. Always make such small calculations in order to get an idea about how real your model is, all right? 700 to 100 kilometers per hour is pretty much, all right? But we will have an idea. So the speed that we're applying now is this one, 200,000 millimeters per second, yes? This will be the... Let's delete here because it's not correct. Let's write velocity, all right? Velocity. Because we cannot somehow convert or translate directly from x to distance to velocity, all right? Let's do something correct. So this is the correct calculation. I'm sorry for some mistakes. They are ad hoc. They are not prepared. As I said I usually say in my description of the movies, of the streams, there. Let's say I'm kind of unprepared. Okay, so I only know the topic. I didn't make the calculations beforehand. This is why sometimes small errors occur, but we usually rectify them in time. No, absolutely no problem. So back to here, if we write 2e5, then we're done. All right. Let's see the direction of the vector. Perfect. As I told in my calculation, the target at this moment is to have 0.001 second. All right. This means we are going on detail and write 0.001 seconds, the end time. All right. All right. Before doing more, let's fix the bottom of the tank. Fixed. Apply. Back to analysis settings. We're not at this moment. We're not doing anything else. All right. Maybe just for fun, here make retain inertia no, and out here to make it like a slow, let's say slow motion to have more frames. I will make it here 100 result number of points. Let's leave it like this, like a beginner, something very quick, and we can see what to correct then and how to evolve this problem, which now is not correctly implemented, but you'll see where the problem is. So we have everything Lagrangian at this moment, yes, but the topic of the presentation is coupled Eulerian-Lagrangian. Yes, we will go for Eulerian in the next minutes. So please have some patience. Save. We have the velocity, it's fixed. Maybe, you know what, just for fun, let's also assign some gravity, all right, minus y. This is the gravity. It will be nice when the speed is too high, the gravity is not necessarily very important. But if we extend the solving time, the end time, we can also see the water come back. All right. All right. Save again. And solve. Let's make like a prediction, because I didn't leave that bonded contact. Maybe it will do like a jello, and maybe it will develop some tremors. All right, maybe I don't know. I didn't do such approach until now with Lagrangian, with Lagrangian water. Yes. Let's see what will occur when we leave only frictionless body interaction. Solve. How much time will it take to solve? We're going here on solution information. 14 seconds. Yeah, we can wait 40 seconds. We have this time. Why not? This is the FEA. This is how the FEA should be done in the beginning, with small, very fast iterations in order to localize and to see where the errors are, where the problems are, and the lack of conformity. All right, you'll see in a few seconds. Look here. Let's animate, and we have something like this. Should we extend the end time? Let's extend the end time at this moment. Maybe make it 5. You know what? Yes, let's make it 5. Solve again, because it takes so little time to solve. We can afford to extend the end time, no problem. Clear generated data, yes. solve. Clear generated data, yes, and solve. I will read the new messages if they are. I will read them in usually in my spare time, let's say, yes, while the FEA is solving. So please have some patience if you have asked some questions on the chat. Yeah, here it needs to be interrupted. So Control-Alt-Del, Task Manager. We're looking for this one, for the solving executable, which is something like Autodyne. Can we see it or not? Let's arrange by name here. Autodyne, ANSYS solver, and task. And we kind of killed the process, the solving process. Or let's also end this one. Clear generated data, yes, and solve again. So it takes, I don't know, 25 seconds. Let's read if there is another question. It's Mr. Murat. Hello, sorry, yes. I thought you wouldn't even look at the messages. Why not? Would you run a vehicle crash test with DLS Dyna? Yes, not today, because it's not the topic. Could you direct me to a place where I can receive some help? Yes, this is the place, okay? You know, because we have precious time, please, yes, write me an email. And if you are willing to donate a coffee or two, yes, I can help you develop your scenario more. Yes, we can do it. Yes, I am reading. We can work. Mail me. On my website, expertfea.com, you have the contact page, so mail me if you want. I'm sure that we can do nice things, okay? Also, some small questions, coffee is okay. Some small questions or principle you can ask here, no problem, okay? And if I know the answers, I will reply. If it's something in detail, if you have a model, a scenario, something that you are stuck at this point, then we can, exchange some advice for coffee, and I can work for you, no problem. And it will be affordable, no, absolutely no worry. So save. Let's see what happens. Something like this, okay? It looks cute, yeah? It's wrong, but cute. And we have a proper contact, let's say, with the tank walls. This is a beginner simulation, yeah? What we need to do more? Firstly, if we are going to keep this, we will need to, right? But of course, we're not going to keep this. We're going to develop it further. Let me see one thing for comparison. All right. Let's duplicate this. I can close basically at this moment. This is the FEA for the airplane which touches water. It will be like an example for me. This is why I'm keeping it here in if I get stuck in the near future. This is the ball on water, and I will say that the setup is all Lagrangian, and here we are going to have Eulerian-Lagrangian, as it should be, all right? I'm thinking. All right, double click. Performing simulations in LS-DYNA, yeah, it's more complex. Okay, it's the original software is not user-friendly, or it's not beginner-friendly. Thank God, in the last years we have nice implementations of LS-DYNA in ANSYS. But it's still on a, let's say, on a primitive level. Experts can make some miracles appear here, but yeah, it's pretty complex. So in the sometime in the future, we will also do Eulerian-Lagrangian with LS-DYNA. Yes, let's have some patience. Following the topic of this simulation, let's change from Lagrangian to Eulerian. All right, virtual frame. This virtual frame, and the immediate difference is this one. When you click analysis settings, you can see that we have a virtual frame where the Eulerian bodies, which are fluids, yes, liquids and gases, these are fluids. They can exist in this frame, in this virtual Eulerian frame. You can ask yourself, why is it so big? Because we only have water here. It's so big because maybe due to splashing, there will be high waves. Yes, and we need to see them. So let's leave them like this. Now, where to edit this Eulerian frame? Here. We have Euler domain controls. This frame is scoped around all bodies. In the future, we will scope it only around the Eulerian bodies. But now it's scoped only on the entire bodies, around all the bodies. Do we predict that we will have some water outside the tank? Not on this plane, not on the XZ plane will not predict that will be some water in this simulation. This means we can decrease the scale for the X and Z axis to be 1 in order to regen you. And you look here, all right? We do not predict water to be outside the tank. And maybe a little, maybe let's decrease here a little. 1.1. All right, and why not? Let's make it 1 also. It's not necessary to go for the entire assembly. Yes, at any given time you can make it 0.5, 0.5. Yes, and you'll have almost half of everything. All right. I'm sorry, I meant this thing 0.5, like this. Come on, you don't want to cooperate. All right. Yeah, it's correct now. Where are we? Here, 111. Yes, we have enough space for the splash. And if we're going to stay with the default value, the solving time will be too much. Let's just let's solve and watch the solving time. All right, look here, solve. Yes, 50 minutes, okay? 35 minutes. Even less, all right? It's while it's not so long to wait, yes? Let's reduce a little this number from 250,000. Let's reduce it to 150,000. And here now we're going to watch a little the resolution, all right? Now somebody can ask, hey, Claudio, what about this Lagrangian mesh? This is a Lagrangian mesh. Do we care? We care about this. Almost zero regarding the fluids, all right? What I want to say is that let's make the sizing of the water, Control B. Let's make the sizing, not phase sizing. Come on. Let's make the sizing of the water, how much? Maybe 150. Yeah, because we really do not care about this mesh at this moment. We entered the Eulerian domain, the Eulerian frame, and this water will be meshed by the intersection of these points. Yes, let me show you how it will be meshed, and you will also see it in a few seconds, in a few minutes. Let me save this because I would like to make some lines, and I want to have correct, very nice lines. All right. So the lines will be something. They will look something like this. Let's change the thickness. Can I change the thickness? Can I? Can I? I don't know if I change the thickness. We don't care too much. But the question is if I can. No, I wanted to duplicate it. So at this moment, I'm explaining in detail how the Eulerian frame behaves and how will the mesh exist, all right, for the fluid. Even though, yeah, it's not very precise what I've done. Let me show you. These are details that you usually don't find. Nobody explains in such detail for everyone to understand. And also this one, this direction here. Have some patience, and you'll congratulate yourself for the patience. Look here, because now at these lines, at this moment, you begin to understand what happens and how the mesh occurs. I don't know what's with this point. I do not care. So there are ANSYS will create small, as we usually say, cuboids. Yeah, small cubes. At the intersection of each lines, there we can also somehow think that are intersections of planes. Then small cubes will result. Yes, you'll see them in a few seconds. You'll see in a few seconds the water meshed as small cubes. You'll see. So I said that I don't care about the mesh of the water. Sincerely, I don't care about the mesh of the tank too much. But yeah, let's not overkill it. What we need to correlate? We need to correlate the mesh sizing of the impactor, also the surrounding tank. We need to correlate it with this mesh sizing or density, yes? And they are kind of the same, let's say, kind of the same. We can even go smaller, 100,000. So this distance, yeah, it's almost the element size, yes, of this and this part. Almost, yes. We need to have conformity, let's say. So let's not keep you waiting so much. Save and solve. So now we exceeded the beginner level. Yes, now we are on the right path. We are using Eulerian frame now. Does it say something? Yeah, no, yeah, perfect. Clear generated data, yes, solve. Any error? No, clear generated data, solve. $11 minutes, 8 minutes. Yeah, why not? Let's leave it. Let's let it solve. Do we have any question? I wrote an email. Coffee is okay. Yes. All right. Coupled Eulerian-Lagrangian. I don't know. Do I dare to write ANSYS? Do I dare? Because not so many people know about this. Abacus, all right. Abacus, something in ASDynamo, yes. But nothing in ANSYS, all right. Except, yes, my simulations. So when I told you that in ANSYS, almost nobody approaches this domain, I told you, yeah, the entire truth. So look here, this is a pretty complex simulation. What we have something like this. We have a toilet plunger made of rubber, like a suction cup, rubber suction cup, and it will push this mass of air. This is air. Oh my God, it's so complex. And this is water. And this plunger will compress the air, which will push the water. It's so complex, but I will show it. Look, something like this. This is air, and this is water. It's complex. You can see also a part. This is air, by the way. From this, it escapes here, air into the water. This is air from here to here into the water. It's I will show it here. Air escapes and pushes the water. Here is air from above. Yeah, you can see there are two phases. This is the air and this is the water. And this is, I remind you, this is a very easy way to perform fluid structure interaction. Yeah. Yeah, this is very complex. In order to look for, to search for a couple of Eulerian-Lagrangian that I made, it's, I abbreviated them. This is the acronym, SEL, couple Eulerian-Lagrangian. And if you search them, ANSYS cell or expert FEA cell, then you can find them easily. Yeah, this is, oh my God, this is so complex. Let's show you something easy. Then something more complex. This is also easy. And yeah, we have this. Oh my God. So this is easy. Yeah? So we have like a wedge. Goes into the water and it will split the water in two. This is very easy. I have done this 5 years ago. This is suitable for a beginner. It's exactly what we're doing now with the sphere in the water. And here I have made like a boxing. I took a boxing glove from somewhere. I don't know. I made it rigid, and I have pushed a water can or something, a recipient with water, and you can see the water going down. This limit, let me show you a limit. This is section view, by the way, because I will show you a limit. This limit here, this limit, because there is a flat face here. This is the limit given by the Eulerian frame. You remember the big cube with the divisions, yes? The Eulerian frame is something like this, and this is the limit of the Eulerian frame. You need, in order to see water going above and beyond, you need to make a bigger Eulerian frame with more cells, more cuboids, let's say, and with an extended solving time. This is the limit of the Eulerian frame. Here, this is the flat face is the limit. Yeah, there are many limits, but this is, of course, 6 sides. But this is where the water goes out, and we can see the limit. There are also limits on the other sides that they are not impacted. Let's say they are not touched by water. Yeah, it's pretty nice. This is a big advantage. Now we're going to have transparency for the fluids. Yes, we have transparency, and it looks very nice. I made the mesh. Look here. This is the. By the way, this is the Eulerian cells, the small cuboids that I told you about. Yes, this is the Eulerian mesh. All right. This is. It was a lot of work here. Yeah, this is the Eulerian mesh given by the Eulerian frame at the intersection of the imaginary points, lanes, and faces which create such cubes, let's say. This is complex. This is very complex. Yeah, this is useful to simulate lubrication. Of course, you need to alter the density and the shear properties in order to obtain some oil and or Vaseline. Yeah. Let's look up the simulation. Save. Yeah, it looks nice. We have it's very nice. We have the option to go in section view, and look here. It reached the bottom and it bounced back, all right? In order to have the water not transparent, you need to access the other solution results. Velocity. For velocity, look here how the water looks like. Let's hide the edges. If we hide the edges, we have a faster animation. Yeah, if we show the edges, you can see those cubes that I was talking about. Yes. Yes, stress in the sphere. I have fixed the bottom of the tank. Of course, that yeah, the values for the stress are very high because I have left a default aluminum. Yes, default aluminum means an aluminum without plasticity. Yeah, watch my previous stream regarding plasticity and Riemann deformation, and you will see there how we apply plasticity. It's very easy. All right, what to do now? We like, at least I like how it looks like. I like how it looks. Should we complicate things more? No, not at this moment. If you pay attention, you can see some small problems here. There is, for example, there is a collision between the water and the wall. Yeah? For example, there is a collision. The model is pretty simple, and the solving takes very fast, let's say. We have the option to make everything, almost everything, as shell, as surface bodies, yes, with zero thickness, let's say. Let's go for the airplane, and you'll understand more when we're going for the airplane. Save. So, in order to have less degrees of freedom to solve, in order to have fewer equations to solve and fewer nodes, we preferably and always we need to almost always, we need to have in explicit dynamics shell parts. Yes, I will drag and drop simulation from 0. And the next scenario that we are doing with the airplane, it will be a shell, an entirely shell problem, yes, with surface bodies. Let me show it to you. Import geometry browse, and I will import the geometry with the airplane if I am able to see it. Come on, show it to me. Airplane, all right. Here we can write airplane, no problem. And water. Engineering data. Let's have the same aluminum alloy and water with some changes. Delete, all right? So let's now avoid the 65,000 megapascals stress. In order to do this, general nonlinear materials, aluminum alloy, nonlinear, all right? As I said a few minutes ago, aluminum alloy nonlinear implies having bilinear isotropic hardening. This is the plastic domain. If we have only the elastic domain, the stress increases too much, yes? We have aluminum for the airplane body. Let's also have some water. Water plus. All right, and we will see. We'll see in a few seconds what we need more. Double click, yes. I will do my best to kind of duplicate the simulation that you have seen in the trailer. So let's see the parts. This is the water. We don't hold the water with the tank or something at this moment. And we have some, these are shell parts, yes? These are surface bodies. In order to have 2D elements, not 3D elements, 2D elements. So let's name them. This is wing. This is, I don't see it. This one is engine. Maybe this one is also engine, yes. F2, I press F2 for renaming, yes, engine. This one is another wing, and this one is the entire body of the airplane, all right? So, water. We know how to define water now. We are experts in coupled Eulerian-Lagrangian. Water, this is water. Wing, everything, body, and so on. Let's define the material as aluminum alloy nonlinear. Now we need the thickness. How much thickness should we give? As I have used in the past, let's something like, 150 millimeter. Even though in reality, yeah, the body of an airplane, it's made of frames, yes? Let me give you a reminder. Yeah, it's made of frames. It's not like a pretty solid, yeah? It's made out of sheet metal on frames. But we're assigning like 150 SS. We're assigning like such a thickness for the entire body, okay? You will see in a few seconds the thickness. Now the thickness is kind of 0 because we didn't make the mesh. Let's see a little. What contacts do we have? Right click, rename based on definition. Water to body. I don't need this contact. Yes, delete. Because I have the default body interaction with frictionless. But I definitely need this contact between engine and wing and body. I need these contacts. Let's deal with wing and body because they will be left like this, okay? And in order to avoid, yes, this is the contact. It's not so cute. I don't know what it's contacting, a small edge or something, you know? Let's extend. So this is the red part, okay, the source, called here contact. Let's kind of extend this, you know? Let's extend it with connection? No. Limits? Limits, all right. Let's see if it works. Limits. And there is here, on this side, on the airplane side, let's click this face, hide body. Let's click this face, all right? Come on. It selects it, but on the inside. If I have a section, like, look here, it selects, but on the inside. This is why it's not easily. From here, it's not easily seen, but here it is easily seen, all right? Or we can make a section. Let's make a section. Come on. Look here, yeah? So I want to contact, yeah, these with this. Can I select, I don't know, can we select the edges only? For the wing, can I select the edges? Let's see. Right click, cursor mode. Face, click, hide all other bodies. And here, let me, I have only, I can select only this face. Why not? Let's select this face instead of 12 other faces. Yes? Show all bodies and we'll have this face, yes, with this face, which is seen from inside, all right? Let's do the same thing on the other wing. So let's keep here this face, click, contact, apply. And here, let's ensure that we have that face. Yeah, it's the correct face, yes? This face, it's the correct face, which holds the wing, all right? Do we go in section view to see? Let's go in section view to have the best transparent, the best clear method, yeah? Okay. You know what? There is this showing on the outside or on the inside. It's a problem of, look here, wing body, of the side, which side is contact and which side is target, all right, and we're finished with this. Let's go for the wing to engine. The engine has, what face has the engine? This face, all right, and it touches this face. I would like to touch even more, even this patch, all right? Let's see if it's possible to include. Click two faces here, and I will include this face. It's not so possible. Can we go for adjacent here? No. You know what? Let's leave it like default, and we will see if it needs changing. Wing to engine, and here is engine to wing. Let's right-click, flip contact and target to have again engine to wing, just for conformity. And then I don't know why this is not selected. Is it possible that there is a gap or a hole there? We don't know. We will understand when we run the simulation. Or maybe after we mesh it, okay? Small remark, because we want the engines to fall off, wing to engine, let's make it breakable. Yes? And let's assign something like, I don't know, 100 and 50 for shear. 100 for normal stress and 50 megapascals for shear stress limit. Wing to body will leave them not breakable, yes. Even more, because these are shells, they maybe do not touch perfectly at the seams here. This means we will need to define like a pinball radius that exists in the static and transient structure simulations. And here we will be pretty generous. Yeah, pretty generous with the offset or pinball radius, let's say, I don't know, 200 millimeter. Mesh, let's give it something for default, but make it here capture curvature no, and quality low. Save. Let's take a small break. I will look a little at my smartphone. No message, all right. And I will look for any questions. Perfect. We have silence. Where were we? Here. These are the contacts, interaction. Let's just generate a default mesh and see where we need to define. So, as I said in the past, this is an Eulerian body. Yes, this means we need to make the mesh, because we don't care about the Lagrangian mesh. We make the mesh very large. Generate mesh, and let's make this failed. This means we need to refine the mesh sizing. Hide with F9. Click one body, Control A to select all sizing. How much should we make it? I don't know, 250? Ooh. I kind of remember these values from what I have done in the past. So now do you see the thickness? The thickness does not exist in the geometry model, but when we meshed, then the thickness appears and is visible because we have assigned this thickness here. For example, if I change this thickness to 300, or no, 500, let's say, you'll see how much it increases. Yeah, you see? This is 500. If we make it again 150, then you can see it like this. All right. You can maybe ask me, hey, why it's like a collision? It's only like an impression, let's say, because from the middle, there is the middle of this is the middle of the shell. So from the middle, we have 50 millimeter offset on both sides in order to achieve the 150 thickness. This is the middle. It's the middle face, the center of the reference surface for the geometry, all right? So from the middle, there is an offset of 50 millimeter above and below. Yeah, on top and bottom, if we have or left or right, yes? This is what you are seeing here. Let's only select all these. Ah, it's not possible. Because there is a 75 millimeter offset, yeah, on the exterior exterior side of the surface, these faces, then we have like a collision, but it's not, let's say, real. It's not a collision, okay? Here, again, we have an offset, yeah? Here we have the middle reference, middle surface, and it is being offsetted with 75 in order to create the mesh. This offset, yeah, will kind of, it will look like it will collide the wing, yeah, but it does not collide in the FEA. So we have all these. Let's assign some of the boundary conditions, okay? So let's now encompass only the water, okay, at this moment. Let's go for Eulerian domain controls. And here, instead of all bodies, I would want to go with Eulerian bodies only. I am not interested on to have it offset. I only need to encompass the water, right? So let's start with 111 with no offset for the Eulerian frame, yes. And do we need this portion of water here? Sincerely, we don't need water here, okay? I need to simplify the model as much as possible. So on the x-axis, I will write 0.8, and it will cut. I was showing with the fingers. I will show with the mouse. It will cut this portion and this portion. Yeah, 0.1 from here, 0.1 from here. You will understand it right now. You see, because I don't need this portion of water. We need only water while it touches the useful portion of water, okay? So, do we need this portion of water? Yeah, let's leave it, because we have the airplane wings and they will appear nicely, let's say. All right. If there is like a small dilemma or a small question that appears now. At this moment, you know what, let's leave everything like this. But if waves will appear, they will clearly exceed this limit, all right? If there will be waves. And because they exceed the Eulerian frame, we cannot see those waves. We can solve this by increasing the Y scale to, I don't know, maybe 1.05. Look here. Let's make it more visible, 1.1. Now we let small waves to appear from the water surface. They will come up. Where is the problem? The problem is here. It offsetted also the Eulerian frames also on the bottom. And I would like not to have this gap on the bottom, because I want the water, the ocean water or whatever, to be continuous. So let's make it with this gap. If I assign standard gravity, yes, minus y, yes, this is the gravity, then the water will have the tendency to fall. Yeah, because it can't exist here also in this gap. The water from here will have the tendency to fall. It will not look so nice, let's say, okay? We don't care if we have this gap, but having this gap means that the water might fall, okay? And I think it will fall. It will fall due to gravity, okay? And we need to, either we remove the gravity, which is not cute, or we leave the gravity in order to have a proper, let's say, wave, okay? So enough with this so long discussion, but these are details that, yeah, they appear and they will come up, they will be solved only with experience. Let's go for the, let's leave these like this. Can I make it, I don't know, maybe 100? And I'm looking at the resolution, yes? I need to somehow correlate the element size, yes? 250. I need to somehow correlate it with the frame, with the discretization. And I see that the water discretization is around 250, okay? We need to be conform. We need to have similar element sizes, let's say. So let's leave these like this. And time. This is a very good question. Of course, at the time of landing, average landing, I don't know if landing may be touchdown speed, landing speed of a plane. I think it will be touchdown. So 260 kilometers per hour. 260. Maybe we'll need to increase it, okay? 260 kilometers per hour. Let's make a small calculation, all right? What is 260 kilometers per hour? Let's make it 250 kilometers per hour in meters per second. How much? Let's have a 70 meters per second, all right? So if we have 70 meters in 1 second. I would like my airplane to travel this distance. Let me show you. Kind of 20 meters, yes, kind of 20 meters. So in my calculation, I will ask, what about 20 meters? How much time do we need? As an end time. This is what I'm calculating now, the end time. So x equals 20 meters multiplied with 1 second over 70 meters. I can simplify this with this. This 0 with this 0. And we have, in the end, 2/7 seconds. And 2/7 is how much? 2/7 seconds. 0.3. 0.3 seconds, okay? 0.3 seconds. This is what I will use as an end time. If I apply 70 meters per second, which is 250 kilometers per hour, approximately, okay? So let's make here 0.3. And let's apply this initial velocity, all right? On all these bodies. I will select only one of them, Control A to select all. Initial conditions, go for velocity. All right, regarding the orientation, I would like to have it longitudinally, axially, yes, from the airplane. How should I select the axis? Let's see. Control F to have a face, and let's select these two faces. Let's see. No? Maybe this. Okay, perfect. Apply. 70 meters per second. This is the velocity. So hard to believe, but these are all the loads, all the boundary conditions. Let's say the water needs to be held somehow. We need to hold the water somehow. We don't need it. We don't have a tank, a reservoir. We don't have beaches, waterfronts. Let's leave it as default, and in the future maybe let's restrain somehow the water in the software, nothing geometrically. Okay. Do we leave them as default? Yes. If the solving is too much, I will apply automatic mass scaling. Here, retain inertia, no, and output controls 100 result number of points. Let's leave it like this. Control pressed, switch to automotive mode, and here some results. Save. Solve. I'm thinking if I'm missing something or not. Rename based on definition. Rename based on definition. Save. All right. Let's solve it, and let's see how long it will take to solve. Only 25 hours. maybe 20, maybe 14 hours, maybe 10 hours. You can imagine this isn't my first rodeo, so I have patience. I know what to expect, and I know how to optimize to shorten the simulation. So let's say we have around 2.5 hours, okay? Of course, we will not wait this much in this live stream, and nevertheless, you are here to learn how to simplify everything, and I'm here to tell you how to do this. There are multiple ways we can decrease the end time, of course. You know, at this moment, let's come with some time steps. Let's advise some time steps. Yes, this is what we'll do. We had 2.5 hours. Let's see what happens if we applied some time steps, out of curiosity, okay? We'll take it gradually. Then we can edit the mass scaling. Then we can reduce the number of Eulerian cells to make a coarser, yeah, a less fine mesh on the Eulerian side for the water. How long will it take instead of 2.5 hours? I think maybe it will take the same. Let's look a little. I'm watching for questions. I'll write, okay, perfect. 7 hours. What do we know? It didn't help at all, my suggestion. Okay, so the time increment is around 3 at the power of -6. Yeah, so this is not useful because it doubled the solving time. Let's leave everything as program controlled. When we had as program controlled, we obtained 0. You need to write 0, okay? 0, enter, 0, enter. When we had everything as program controlled, we had 2.5 hours for solving, yes? So we are as we were. Let's a little increase the velocity. Maybe make it 100. 100 multiplied with 3.6 equals 360 kilometers per hour. A little, an accidental landing, okay? Because what I would like is to decrease a little the end time. All right? Now, where are we? We are at the point where we, of course, we will have a shorter solving time. Let's see how short. Maybe 1.5 hours, maybe. Let's see. All right. So this is the solving time with the current mesh, with the current Lagrangian mesh and with the current Eulerian mesh. This is the Eulerian discretization. All right. So instead of 2.5 as we had before, now we are approaching 1.5. Yeah. So of course we will not wait for 1.5 hours. Let's shorten even more. Clear generated data. My proposal was to introduce mass scaling. Let's see if it does something. So we're imposing a CFL time step of -6. We had a time increment of 3 at the power -6. Let's make it 1 at the power -5. Let's see if it works. All right. Familiarize yourself with the concept of mass scaling. All right. It's always remember to ask ChatGPT, ask whoever you want. Okay. So where were we here? There is also this. Sincerely, I didn't want to show my ChatGPT conversations. This is why I didn't access it. Mass scaling is a computational technique, primarily in a specific finite element, that adds a non-physical mass to elements to increase the stable. I explained it in one of the previous live stream. Okay, feel free to go and ask, and you shall find answers. I asked for such a time step. Let's see if it gives such a time step. If we increase the time step, then the solving will be much faster. I'm looking at the clock a little. Yeah, we're below 1 hour. So the mass scaling worked. Today at our 13th anniversary of explicit.com, everything works very smooth. Let's assume 45 minutes or 40 minutes, yes, and let's go even faster. I will make the Eulerian mesh a little coarser, okay? Mm-hmm. 150, 100. Maybe half an hour of solving. Okay, I would sincerely, I would like to have something like 20 minutes of solving, something like this. I don't know if the engines will be dismantled, will be separated from the body. Let's just see. So I would have wanted to see more. This is complex. Yeah. I made the simulation according, I wanted to see what happened in the Nord Stream pipe. And yes, there are two blast loads, one here and one here, and they crack the pipe. Yeah, and everything is underwater. It's very complex. I'm sorry for the resolution. This is the problem when showing vectors in ANSYS workbench animations. Otherwise, it works. It's nice. Yeah. So here we have concrete and steel. Yeah, you can see the breakage of concrete and steel. All right, let's see how much the solving takes. Can we get 25 minutes? So we have 4 spectators. I need to provide quicker results. We're almost close to half an hour. All right, so let's do it like this. Please have some patience. I will do my best to make it towards 25 minutes. Can I make this mesh a little more coarse? The mesh on the airplane, let's see, 0.25, can I make it 0.3? Now we have how much? We have 11,000 nodes. $8,000 nodes, yes. We're happy. Can I exaggerate a little? Let's see, what are we not doing for quicker solving? Of course, in reality, in your projects, in your company, in your laboratory, you will use finer mesh because you'll have the days and the weeks, the months at your disposal to make a fine, reliable model. Okay, but now I need to show you results in 20 minutes. Okay, so please bear with me. Have some patience. I'm doing it to give you quicker results. You please understand. Maybe also no. I was thinking about shrinking the water here, but no, I would like to have the water at the same level with the wing just for visualization purposes to look nice. We will discuss, I think, in this stream, the difference between flow out and rigid. There are rigid limits or impedance. Flow out means except this phase. Yeah, flow out means that we'll have like an infinite boundary. Yeah, it's like the water that exists in the ocean. Okay. When we have rigid, we will have like a wall. I will show you in a few seconds the other options. There are two other options: impedance and rigid wall. So we're going towards 20 minutes. Okay. Let's leave it like this, and let's also check some FEA from. I cannot show you coupled Eulerian-Lagrangian in ANSYS because almost nobody did. But I can show you. Yeah, this takes place in water, by the way. Yeah. Look here, yes. And the chips, the metallic chips, they you can see how they interact with the water. They create small cavities. So look here. Here, pay attention here. Look here, they created cavities in the water. Here. Yeah. So it was a very complex simulation. And it is a very complex simulation. Yeah, lots of hard work. Before showing something more, let's go and search for ANSYS water. Maybe we see what other people have done. Not CFD, of course. Oh, such a nice animation. It's clear that this is AI. Another AI. Huh? Or is it ANSYS or? We don't know at this moment. ANSYS workbench, hydrostatic pressure, no. ANSYS discovery, no. This is made with aqua, I think. Yeah. Offshore spar wind turbine ANSYS aqua. This is a different domain different from CFD, different from coupled Eulerian-Lagrangian. What we do now and what am I simulating now is kind of similar with volume of fluid in CFD, with this domain, volume of fluid. Okay, we have a trial here. Let's see how it behaves. Oh, energy error too large. So at the moment of impact, the FEA stopped. The question is, why did it stop? This is a good question. Energy error. All right, so the first thing that we can do, and let's see if it works, we can make the maximum energy error 0, okay? We just ignore the errors, okay? at this moment. What is a live stream without errors in convergence, in solving? What is life without obstacles? It makes no sense, no? All right. So this Sir Umut Civici, I think maybe he's Turkish. Water liquid. What does he show? Shear modulus, bulk, specific heat. Judging from here, bulk and shear, I think he made, maybe he made this custom, yes, by himself. Maybe I think maybe he didn't take it from the explicit library, or maybe he has taken it from fluid materials. Is it possible? Did he took it from the fluid materials library? Water liquid. Yeah, I think he took it from fluid materials, and he added, look here, he added these two because they are grade, they are inactive. Yeah, the default is density and specific heat constant, and he added these two, bulk and shear modulus. All right. It's solved. It's solved. Why does the water so? The first sign of beginnership, of amateurship, is the water. Yeah, it shouldn't be any gap. As our master Bruce Lee said, water takes the shape of every container, yes? This is somehow the definition of fluids, yes? So we should be like water, yes? So this water is not so realistic because it will stay in place, I think. I think it will stay in place, and it should, the first thing that should be made, if we were to have gravity, by the way, you see here, there is no gravity. When you apply gravity, the water should fill this space, yes, the surrounding offset. Let's see if it stopped or not. No, it works. All right, and how does it behave? Oh, it looks nice. Oh yes, it looks nice. Let's see the water. This is how the water looks like. Of course, there is no stress in the water, but it's the only way to visualize it as a opaque body and not transparent, as we see here. Let's hope that the engines will dismantle, will be detached from the wings. They might, because, for example, this one has different values. Yeah, and they might. Let's see. Maybe we're lucky. Water, yes, still. He assigned contacts. Oh, he did it manually, and he deleted the body interactions. Why would you do this? You're making your life difficult. He assigned frictionless contacts exactly what the body interaction, the default body interaction does. So there is no use. What? He assigned friction coefficient between the sphere and the water tank. This I can kind of approve, but you need to take into account that we have the water which acts as a lubricant, and the water will kind of impose to have frictionless coefficient between the two solid bodies. Just saying, okay? So, yeah, it's, I would not say it's incorrect. It's kind of correct, okay? Maybe I would have used lower friction coefficients. Maybe. All right, meshing. Yeah, it's a fine mesh. So here, 2e minus 3, 0.25 maximum energy error. Why did you put that value? Why? Default is 0.1. Why? All right. Speed. The speed is 40 meters per second. 40 meters per second, 130 kilometers per hour. A small problem would be, I think, the vector is a little too parallel with this edge, and I think the contact is not made here, and maybe the contact is made too far away because it's not so inclined. Let's see. Okay, now, yes. So now the vector is inclined. He what? He changed the velocity values during the simulation. Why would you do something like this? He changed the direction of the velocity. Oh, and at the end he made it parallel. Why? Come on, why? It's not realistic, let's say. He fixed the tank, yes, I agree. Solution information. 75 minutes, by the way, yes? 1 hour and a quarter, 75 minutes. And of course, what you see is everything is Lagrangian, yes? Look, the reference frame, everything is for the water. Reference frame for the... What? He didn't? Let's see the water. This is the water, Lagrangian. Lagrangian, okay. As I made in my first simulation to show that it's not the correct way. All right, let's let it solve. Now he has no results. Why? It solved, but he has no results. Animate, please. Yeah, cute, yes. Nice try, buddy, but yes, it can be done even better. Let's see what happens with the simulation. I think we might lose an engine, I think, if we're lucky. Yes or not? I don't know. Let's wait and see. I'm wondering if this is made with the Eulerian frame. Let's see. Let's see. By the way, nothing in doing what I present, yes? Nothing with coupled Eulerian-Lagrangian that I'm showing. Yes? We can say that I'm a kind of a pioneer. Yeah, nothing. The only thing left to do is to show my simulations, yes? Do you have any question? I will write an email, okay. Let's see here if he or she uses Eulerian frame. Explicit materials, aluminum, and aluminum, copper, stainless steel. Okay. What? So you're bursting only due to pressure, I think. No explosive. Why? Come on. Why no explosive? Why? Structure steel. Come on, change it to something softer. Aluminum, okay? All right. Analysis settings, no load, no. 1E minus 3, yes, and fixed, yes. He's hiding something because he wants to apply the pressure, I think. Or maybe he fixes it. Force? Why? Why do you apply a force there? And now a pressure, but where does he apply the pressure? I'm interested. Come on, show me. He left now. Maybe he's answering his phone call. Come on, no, please. You have, dude. You have here extend, and you select adjacent. It's right here. Sometimes it's very hard to select the faces as you're doing now manually, especially this face. Come on. All right, let's see the pressure, because look here. Here's such a thick. I would say that is around maybe 10 millimeters or 8 millimeters thick, and it's metal. It's very thick. Let's see the amount of pressure. 30 megapascals. 30 megapascals and such a thick recipient. Yeah, I'm interested. So he solved it. He's showing the cap. Show us the cap. Yes. The cap is made of aluminum. 3 millimeter. This is no bursting with 3 millimeter. No. So he needs to exaggerate the pressure. Yes, we don't care. Let's. He changed the. He changes. No, he didn't change. To 35. So small. Such a big difference. I don't understand the pressure of the force, the meaning of the force, the significance. Why do we have that force? What's the use? There is no explosive. So it's not coupled to Eulerian-Lagrangian. It's a sudden pressure, which, of course, the explosion does exactly this. The explosion exerts a sudden pressure. Six minutes. Yes, your patience will pay off, my dear viewers. And we have engine dismantling. Yes. This is victory. The engine comes off. All right. Because I left these conditions as flow out, it filled the entire space. And there is no wave, I think. Yeah, there is no wave. Let's see my example with the airplane. Let's see. Come on. Here we have waves, yes? And both engines, okay. Oh, it looks so nice. So I didn't make a 100% duplicate. We have waves. What should I do? To have more realism. Let's save it. Then we will modify it a little. Sincerely, I would like for you to see waves, and it looks much nicer. So nice. So yeah, this is also a nice simulation. Coupled Eulerian-Lagrangian. Yeah, it's nice. You can see the bottom flexible. Very nice. Energy strain. All right, and yes, we will treat the SPH, the small spheres. We will treat them in another simulation. This is cute. I need to show you the rocket because it looks so nice. This is also nice. So this is a boat being launched on water. It's like a drop test on water. I made multiple scenarios. There are 3 scenarios. Look here, in one of them the boat floats. I modified, I think, the initial velocity of the drop, let's say. It floats so nicely. Now it's the initial velocity is highly increased, and this is why we have a lot of deformation and shock there. Let's see here. So here it's like an amount of water, like a tsunami, let's say, amount of water falling, cascading, yes, from a, I don't know, mountainside or something, is falling onto a parking lot, and it's moving the cars away. They kind of interfere here because I think they are not a shell. There is a philosophy with the shell, and I will show to you now. I will explain to you. The shell will always leave a gap. Yeah? This is a shell body. It will always leave a gap, the shell. We have waves. Only the distance between the water and the Eulerian flame is too small. This is why the waves are cut. Yes, the waves are cut here by this face. In the simulation, the waves are higher because I left the waves are higher because the limit, the upper limit of the Eulerian flame is higher. There is a bigger offset, okay? And the waves can exist, can take place until it hits the limit of the Eulerian flame. So yes, I will increase a little the top side of the Eulerian flame, and to see if we have higher waves. Yes, because this FEA it just finished. Let's solve it. Let's animate it. Yeah, it looks something, okay? It's not perfect because I have done this in 1 hour or I don't know, 20 minutes and 1 hour and something, okay? I didn't really think too deep about this. So what we need normally, we would need to extend the end time at least to 0.25 or 0.3. And you see the limit of the Eulerian flame. This is the limit, so we need to increase to make this side, we need to make it higher. Yeah, it looks so nice. Let's make this limit higher and more coarse mesh in order to have an even faster solving time, because I'd like to close the stream soon. Duplicate. Do we have any question? No, perfect. I can show to you something like this. I will write to you. Where are we? Here. All right. You know what? Let's extend the time to 0.25 and decrease the cells. 0.25 and decrease for instead of 1.1. Let's decrease also on z-axis. To have something like this. This is the useful amount of water, and let's make these instead of 70, let's make them 40,000, yes? Out of curiosity, I would like to see in my previous simulation, the one that you see on YouTube, I would like to see what conditions I have put for the, let's say, rigidity or the boundary conditions for the water. Let's see here. Flow out. It stays also flow out. All right. Yes. Instead, here I have made a manual frame. 55,000 cells. Yes. The solving time was. Do I have a solving time? No. Back to my simulation here. 40,000. Only the proper amount. Should I do this? 30,000. All right. Save and solve. Yeah, I wanted to increase here 1.2 to have bigger waves. Sincerely, I would like bigger waves. 25, why not? Save. Let's see how fast will it solve. If we have 12 minutes, if it will be 12 minutes, then we're going to be golden. Let's make it 12 minutes, okay? This means we will revert to 0.2. And here, 0.6. Maybe it will be 40 minutes, but yeah, we don't care about such details. These normally are simulations that should be made in dozens of hours. So yeah, what we're presenting now, it's perfect for the purpose of this tutorial, of this live stream. My purpose is to attract people, beginners, in order for them to apply and to like this domain, because it's very interesting and it's always fascinating, and with new results, new solutions, new approaches, new scenarios, new facets of the same problem or different problems. And we can go so much into detail, and yes, my purpose is to attract people to do more than just some drawings and some models. Okay, it's so fascinating to see the 3D models animate and do something else. Of course, if you double it with experience, with knowledge, with theory, then yes, it will be extraordinary, and you can somehow understand what we feel, we, the simulation engineers, what we feel when we feel lots of satisfaction when we see such nice results. So this is a kayak sportsman. He's being launched, and yes, there are two cases: when he kind of stays under the water and when he floats. So you can see here the limit of the Eulerian domain. Yes, this is the limit, so it cannot exceed here. Okay. The great news is, even you don't see it, when he stays under the water, he has a mask, so he will not suffocate. Please don't think he will drown. No, he has a mask. He's also holding his breathing, and he survived this. Yeah, so this is why I wrote here succeeds, because he's a survivor. Believe me. Yeah, lots of work. All right, how much does it take? 60 minutes. Okay. Do we have a notable change? Yes, we have higher waves. Yes, they can get much higher, but they are hitting the limits. The waves are a little higher. Okay, bear with me a few more minutes, 15 minutes, and we'll have. Now you see. Yes, what are you saying? Because the Eulerian frame is under the Eulerian body, or it's offsetted, then the water falls. I will not say drip, it falls down due to the gravity. Yes. In order to alleviate this problem, this frame should be exactly touching this face. Okay, this limit should be exactly touching. But why doesn't it touch? Because if it touches here, it will also touch here, and we have no waves above water, and we need these waves. This is why I didn't complicate the FEA. Normally, it can be here instead of program controlled. It can be selected manually, and we can impose our own dimensions and limits. And when we impose our limits, we can perfectly touch these frames and leave also the gap that we want. But I chose the easiest way for the software to describe, to impose the limits. I only changed them in a symmetrical manner. Yes, these are symmetrical to the center mass of the water part. Yeah. So, for example, this we're on the axis Z, let's say. All right. So this means if somehow the mass center of the water, we're talking about the Eulerian body, yeah? The water is the Eulerian body. If the mass center, and it is, the mass center is somewhere here, okay, at the intersection of the diagonals, here, where the cross is or the minus. Then, if we're on the z-axis, we have 0.3, 0.3 whatever on the minus z and 0.3 on the plus z. It's like a scale, it's not a dimension, okay? 0.3 here, 0.3 here. If we're going on the x-axis, for example, here, and we have the mass center exactly, should be something like here. Comparing to the mass center, we have 0.4 on the minus direction, 0.4 on the plus direction, yes? Something like this. We need to think how the software applies this, okay? It's kind of hidden or virtually applied. And then on the y-axis, this is the mass center is somewhere here, and there will be the half of 1.25, 0.625, up and down, yes, minus 0.625 plus 0.625 on this axis. Don't be fooled about these values, because they are not distances, they are related to the main dimension of the Eulerian body. So yeah, it's a lot of knowledge and philosophy to know and to take into account. I know all this because I have years of experience in this domain. 10 minutes. All right. So, but how does it behave? Oh, yes, we have nicer waves. Okay. And because I don't have that the touching limit, there is an offset. This is why the water falls, let's say. But now it behaves much nicer, let's say. I will let it end, then we'll look at the results and end the stream then. Okay, so what we have here, we have an explosive which is detonated in the water, and then it propagates, it launches the boat in the air. So we have kind of three phases, you can say. Here are the plume or the exhaust gases from the detonation, from the explosive. Yeah, it takes place, it will exist, it's created in the water. Then it propagates this boat up. So some of the plume, the exhaust gases, penetrate not only the water but also the air. So here we have something like three phases: the plume, the exhaust, the gases, the water, and the air. And here you can see the air penetrating where it sees an opening, it fills it. Okay, so it's coming into the boat. Note the gap between the shell body. This is a shell body; it's not solid, and the fluid. Note this gap. This gap is a function of the scaling of the number of Eulerian cells. The more Eulerian cells, the finer the Eulerian discretization, the tighter or less, the smaller the gap will be, because it will approximate better the body that it fills, the cavity that it fills. Okay, so a solution in order to decrease the gap would be to refine and increase the number of cells for the Eulerian domain, for the Eulerian body. It's very nice. Here you can see the entire Eulerian domain, yes? It's very clear, yes? It's so nice to see the discretization of where the fluids can exist, okay, in this Eulerian frame. Yeah, so nice. All right, and this is one of my favorites. I worked a lot on this. I would like at this moment to show you some of my mentors, let's say, or my inspiration sources. There is this website, which I like very much, this one. They are extremely professional and experts in LS-DYNA. They are working only with LS-DYNA, at least on this website where they show. And I admit, and I don't hide it, that I take great inspiration from what they do here. And you need to take into account, I only judge only the animations, the results. I don't know what's inside. I don't know if they present do they give the files? I don't think they give the files. Let's see if they give the files. No, they don't give the files, of course. Right click, translate to English. And this is yes, this is arbitrary Lagrangian Eulerian. It's exactly what we're doing. Only they call it not CEL, but ALE in LS-DYNA. Arbitrary Lagrangian Eulerian. Here there is an explosive part, that is a detonation, and the surrounding air. So this website is overwhelming with what they have. There are so many domains and simulations to learn from, and periodically I go to this website and I take inspiration to do some of my work. Look also this one looks very nice. So there is the plume, the exhaust gases, and the water in the surrounding air. And this is the Eulerian limit, yes? This one, this face. It's the Eulerian frame limit. Very nice. Very. They also do structural, they do so many things. Heat transfer for disk break. I will only look at arbitrary Lagrangian Eulerian, but feel free to look on more of their FEAs. They are extremely knowledgeful. Yes. So the website is lensmore.jp. Let's see. So they are they are pressing I was wondering if there will be a pressure due to the air. So the air is compressed due to the crumpling of the bottle. it's pretty nice. I need to do something similar in the future. There are also some proofs of concepts. I have done a simulations also with water droplets, rain droplets. Let's look for Eulerian-Lagrangian. They have so many nice things. Here is Eulerian-Lagrangian. The sphere touching the water that everyone is showing, but I don't know if it's Eulerian-Lagrangian. It looks like arbitrary Lagrangian Eulerian. Let's see. Yeah, for a while, for a second, I thought maybe it's SPH, maybe smooth particle hydrodynamics. This is SPH, for example, yes? Smooth particles. I will not show at this moment. We will come back to this website in the next live streams. SPH. Structure, oh, this is nice. 1 minute. Excavation. Brittle fracturing of glass. Oh my God, it's so nice. It's so nice. Oh my God. I would like to see this sloshing. By the way, the tsunami. I took the inspiration of tsunami, about tsunami from this website, only by judging their results. This is like a seismic simulation or something, but it's too slow for my taste. So this is the tsunami, which pushes maybe some tanks, but they are held in place, they are fixed. This is something spectacular because the tank is being they are breakable, these contacts between the wires and the pillars and the floor. They are breakable contacts, maybe. Yeah, this is very nice. Let's see how we're doing. So 50 frames. Yes, it should have been extended, but it's perfect for today. The engine is flying away. Let's see. Yeah, it's very nice. In order to decrease the gap, I told you we need to refine the Eulerian mesh by increasing this number of cells, yes? These ones. I have worked maximum, I think, so there is like a common sense limit, 1 million cells. I have exceeded it. I think I made simulations with 2 millions, but yeah, it was, let's say, slow to solve and slow to animate. And so in principle, we should be good with around 100,000. Yeah. So 250, the default, 250,000 should be like a maximum in most cases, okay? I would like to show you how to insert the vectors, and I will close this. So when clicking solution, you have the worksheet button, and here you have displacement, velocity, and acceleration vectors. I will select only displacement and velocity, right-click, evaluate the results, because I'd like you to see those vectors. Which one is more interesting? Let's also put these ones. Because maybe they do not tell you too much at this scale. Yeah. If they do not tell you too much, you can edit them. Look here. Vectors, click, and you can increase their length, something like this. Let's see. All right. Something like this. There is obviously a discrepancy between the moving part and the fixed, or let's say the relaxed water. Okay, this is why there is a difference in scale between these types of bodies. And in order to understand more, let's see if I animate what will happen. Yeah, it might be a little confusing. In order not to be confusing, you need to kind of show them or them separately. Okay, duplicate without results. For example, if we're interested now only to see the velocity vectors only in the water, then look here. Yeah, and it will be more conformal, scaled up. Okay. Also regarding the values. All right. Let's go for meters per second, because I would like here to scope maybe for 40 meters per second. We have this alignment exactly at the intersection of those cuboids, of those small cubes, yes? But we also have this grid alignment, and it's something like this. The most realistic way to view is element aligned and not grid aligned, let's say. So what is nice, even this one, let me leave you with this one. Of course, if there is no other question, no, absolutely. Thank you all for your audience, for having the patience in this stream. And yes, let's hear you next time. Thank you for the support and for these 13 years of cooperation in finite element analysis in ANSYS. Thank you. That's all. Bye-bye.